Welcome back. This is COT 3100. Today's topic is applications of propositional logic. We learned about the proposition. We said any sentence that states a fact, whether that sentence is true or false, is a proposition. And then we looked at these connectivities, AND gate, ANDs, ORs, exclusive ORs, and all of those. Now we want to take a look at some of the applications of propositional logic. In this, the summary of what we're going to discuss is translating English to propositional logic, which some of us, actually most of us, have seen it in digital foundation course, that how we do translations, and we're going to practice that. System specifications, whether it is always consistent, is it true or not. Then we're going to look at the Boolean searching. Boolean searching meaning we use those connectivity signals such as ANDs, ORs, and to make searches. Most of these search engines, such as Google, use some of these connectivities to produce the results of your search. Then we're going to look at some logic puzzles and logic circuits. And this is what we're going to look at in this lecture. We know that in any language, any natural language, whether it's English or any human languages, it's not a language of precise. When we discuss about designing a circuit, or we are going to discuss specifications of a certain hardware or software or anything that requires precision, then natural languages do not do justice, and sometimes it may cause some confusion. It's not impossible, but it may cause some confusion. In order to make that, to get rid of the ambiguity and make it clear, we partition these English sentences, and we come up with these small pieces, and we turn each one into a proposition, and then we put them all together, and that becomes compound proposition. If you connect two or more propositions and state them at the same time, then you have a compound proposition. In compound proposition, then we can check the accuracy of the sentence that we are using, what we are saying. That's how we can check and make sure that what we are saying is absolutely correct. So, the steps to convert an English sentence to a statement in propositional logic is: first, you identify atomic propositions and represent using propositional variables. For example, if I say the water heater is not working, right? That is just one proposition, because it's a sentence that stating a fact. Now, that could be true or false, meaning whether it is working or it's not working. But I'm saying something, and that is considered a proposition. Now, if I assign a variable to this proposition, let's say P, then we call P a propositional variables. So we identify these sentences within an English statements, and we assign them a variable. Identify atomic propositions and represent using proposition variables. Then determine appropriate logical connectives, meaning ANDs and ORs. Here's an example. If I go to Harry's or to the country, I will not go shopping. All right? Here, we look at them. If I go to Harry's, so I go to Harry's is a sentence that's stating a fact, stating something, that if I go to Harry's. I can assign a variable, propositional variable P. Or is or. So the country, I go to the country, it would be Q. If I go to Harry's or to the country, so I go to the country will be a propositional variable Q, then I will not go shopping, or I will go shopping. All right? That is another proposition which assigning propositional variables are. Then we can take this using the last part of our lecture from last class. Then we're saying if P or Q, then not R, right? If I go to Harry's or to the country, then I will not R. R is I will go shopping, right? So that would be P or Q. Then if this, then not R, meaning I will not go shopping. And this is the way we basically take these sentences, convert it to logic, and then we work on the accuracy and correctness of these statements. Then that is how we can start building, let's say, a security system for a car or for a house, or we can build a traffic light, or we can run an elevator, or we can do many things, or control an airplane's wing, or we can do a lot of things, design many concepts in hardware or software using this proposition. Otherwise, by just saying the English, we may have a problem. But here is the issue. How do we check the correctness of this one? We use the truth table, because the truth value of this has to be what is the desirable output that we are looking for. So we put them in the truth table by assigning them true, false, false, true, or 0 and 1, and then we evaluate these values and we say, okay, the truth value is correct, so this statement is correct. So this proposition is correct. Example, translate the following sentence into propositional logic. Here's the example. You can access the internet from campus only if you are a computer science major or you are not a freshman. First, what do? We go to the atomic sentences or the propositions. You can access the internet from campus, right? 1. You are a computer science major. Another one. And then you are not a freshman, or you are a freshman. And then here's the one solution. There are many ways to do it. Let A and C, let A, C, and F, right? There are only 3 propositional variables here, represent respectively. You can access the internet from campus, that's A. You are a computer science major, that is C. And F stands for you are a freshman. So access, if access, then, all right, you can access the internet from campus, then you are a computer science major or not a freshman, because we said you are a freshman would be that, or not a freshman. System specification. System specification means that we check the correctness of all of these logics, that the propositions that we are creating by translation. We want to make sure there is a consistency between them. We want to make sure they do not, none of those logics contradicts the other one. How do we do that? By checking their truth values. Here's the sentence from the book. system and software engineers take requirements in English and express them in a precise specification language based on logic. And then we check their truth values to see if they're inconsistent or not. Expressing propositional logic. The automated reply cannot be sent when the file system is full. So we have two sentences here. One is the automated reply cannot be sent. The other one is the file system is full. So one possible solution, let P denote the automated reply can be sent. We cannot say cannot or say can. Then for the cannot, we just and P, we say, such as here, and P. Let P denote the automated reply can be sent. And Q denote the file system is full. If this file system is full, then the automated reply, since it's not, cannot be sent. And we check this one. We see if Q is true, then this one has to be false. Meaning if the file system is full, then automated reply cannot be sent, right? That is the meaning of this one. Consistent system specifications. Definition. A list of propositions is consistent if it is possible to assign truth values to the proposition variables so that each proposition is true. As I said, you put them on a truth table and then you check it out to see if it is true or it's not true. Here's one example. Are these specifications consistent? The diagnostic message is stored in the buffer or it is retransmitted. The diagnostic message is not stored in the buffer, meaning it is retransmitted, or it is retransmitted. If the diagnostic message is stored in the buffer, then it is retransmitted. All right? We have three ways of saying what we just said here. Right? Three statements. So, let's P denote the diagnostic message is not stored in the buffer. Right? Let's Q represent the proposition the diagnostic message is retransmitted. Then the specification can be written as P or Q, all right, because the diagnostic message is stored in the buffer or it is retransmitted. So this is P, this is P or Q. This statement says the diagnostic message is not stored in the buffer. Is not stored in the buffer. So P, then Q. And if the diagnostic message is stored in the buffer, then it is retransmitted. Well, I'm sorry, the diagnostic message is not stored in the buffer because we said what? We said that P represents or denotes the diagnostic message is not stored in the buffer. So the diagnostic message is not stored in the buffer. So that is negated P or not P. And the sentence said to the third one, if the diagnostic message is stored in the buffer, then it is retransmitted. P, then, if P, then Q. So when P is false and Q is true, all three statements are true. So the specification is consistent. Meaning, if we put these values, we assign true or false to all these propositional variables, then we put them in the truth table and we check them out in what condition all of those three propositions come true. And those would be if all these three statements, all these three things, if they come true, then we look at the values of the variables in there. And we notice that when P is false and Q is true, then all these three are true. And in order to show you how we could have a wrong one, not a consistent one, let's add another sentence. What if the diagnostic message is not retransmitted, is added to these three statements? Then what happens? Now we are adding not Q, and there is no satisfying assignments. So the specification is not consistent. That means if I put this any variable, not Q there, then I am not going to have consistent, meaning output of this one is not going to be true when P is false and Q is true. So if this one comes true, one of these guys is not going to be true. So there is no consistency. So by setting up a table, assigning these variables, zeros and ones, or true or false, all right, and then performing this operation, P is true, Q is true, the output is true. P is true, Q is false, the output is true. P is false, Q is true, output is true. P and Q, they both are false, then the output is false, right? So we're not interested in that one. So P and Q, whether they both have to be true or one of them has to be true, all right? So if Q is not true in these statements, while we know P is not true, then it cannot be, we cannot have a true value, because if they both are in OR, one of the variables have to have a true value, otherwise the output is going to be false. So these two both cannot be false in order to have the true value, the same consistency for all of them. So this one creates inconsistency. Clearly this one, the logic doesn't match with this statements. Logic puzzles is the puzzles that we came up originally by Raymond Smullyan, and he created these puzzles. This was the beginning of the logic, the science of the logic, that we later on we used them by a number of the scientists, and we turned them into what we have as a digital world, right? So, and he started using these logics and creating puzzles that we could solve them. Here is some example. An island has two kinds of inhabitants: knights, who always tell the truth, and knaves, who always lie. You go to the island and meet A and B. You meet two inhabitants. A says B is a knight. All right. The assumption is that here, that A always says that the knight says the truth, and the knaves always lie. So then A says B is a knight. Now we don't know if A is a knight or knave. If it is a knight, then that means B is a knight. B says the two of us are of opposite types. So B is saying that if I'm knight, he's knave, or if he's knight, I'm knave. However, I don't know if B is a knight or knave, so I don't know if he's saying the truth. What are the types of A and B? We are trying to solve this one by just logic, just thinking about it and solving this issue. Here's one way of solving it. We can solve it just by thinking it that way. The only way to solve this one is to take these statements, English, turn them into the propositions, put them into the truth table, and examining the outcomes, and to see if there is a consistency. And then we know which one is going to be true, which one is going to be false. Just like the previous example, we said the only way we're going to get those statements correct is when the P is true and Q is false, for example, right? Here we have to see what it says. So let P and Q be the statements that A is a knight, right? The first one. A is a knight and B is a knight. All right. So P is A is a knight and Q is B is a knight. Then not P represents the proposition that A is a knave. Because if it's not a knight, we said there are only two types. If not P, if P is A is a knight, then not P would be A is not a knight. Since there are only two types, so it is a knave. And not Q, that P is a knave. So if A is a knight, then P is true. All right? Since knights tell the truth, Q must also be true. All right? Then P and not Q or not P and Q would have to be true, but it is not. So A is not a knight, and therefore not P must be true. You see, here we are saying if P is true, and that bit not Q, or P is false and ended with Q, would have to be true. Since we say or, so one of these have to be correct, right? But it is not. So A is not a knight. And therefore, not P must be true. Not P, meaning A is a knight, has to be true. Not P, A is not a knight, so A is a knave. If A is a knave, then B must not be a knight, since knaves always lie. So then both not P and not Q hold since both are knaves. So that both of them, in this case, we realize that they both of them are type knaves, not A, because we couldn't establish a true value between them. Here's the logic circuit. Most of you should be familiar with this. 0 represents false, 1 represents true. We always can create by using some number of gates, such as AND gate, OR gate, or inverters, for example, or there are a number of other gates, and create compound propositions, which really, that's where we get the help. That's where we get the application. That's where it becomes useful. And that's how then we look at it. Of course, this is studied in chapter 12, but we're just going to look at it very briefly. So more complicated digital circuits can be constructed by combining these basic circuits to produce the desired output given the input signals by building a circuit for each piece of the output expression and then combining them. For example, here, it's not kind of clear. This is AND gate. The input to that one is P and not Q. So what do we get? P ANDed with not Q. And here we get R, not R. And they are ORed, so we say P ANDed with not Q or with not R. And this is about artificial intelligence, which we're going to discuss later on, and there's no need to look at them at this point because most of you guys do not have any backgrounds that explains the artificial intelligence, so I'm not going to go through it at this point. Later on, if we get time, I will discuss expert systems and artificial intelligence, which helps us in many, many applications. And we also look into the representing the electrical systems in propositional logic. So, for example, we need to represent our common sense understanding of how the electrical system works in propositional logic. For example, if L1 is a light and if L1 is receiving current, then L1 is lit. So we say lit underscore L1, then light underscore L1, and it with live L1, and it with OK. Also, if W1 has current and switch S2 is in the up position and S2 is not broken, then who has current? And we go through this one. So these are the knowledge base, some of the electrical systems, which I'm not interested in this for you at this point. I'm going to stop at this point, and our next topic, next lecture, will be also released today or tomorrow, would be the propositional equivalences. Have a nice day.